Continuity equation in cylindrical or polar coordinates. By consideration of the cylindrical element control volume as shown below. So use the conservation of mass to derive the continuity equation in cylindrical coordinates. To derive the continuity equation in polar coordinates, first you need to draw an element like this. So this element is actually come from this figure. You just imagine that we have a fluid flow in rotation direction like this. And then we cut or we focus on element that occur at this part only. So the idea to cut this element is we imagine that from an origin here, so we draw a straight line parallel with to the radial, and then we take this element as our focus element for calculation. So this is the 3D of that element. So we could say that the distance here is delta r, or the distance until this point is r, or equal to the radius of that circle, and from the center point here to this point is r. From the center point here to this point is r plus dr. So means the difference here, or the length for this element, is dr. And for this height, so this is the z-axis, so we could write this is the height of z, and at this point the height will become z plus dz. It is mean that the distance here is equal to dz. And the last one here is the distance of this one. So the distance of this one, so we could calculate by using the idea of radian times angle. So the angle here, if we have angle at this area is theta, so the angle at this point is theta plus d theta. Means that the angle for this opening is delta theta. For polar coordinates, we have three coordinates like this, so which is the radial axis, which parallel with the radial direction here, and the Vz, the thickness of the cylindrical or polar coordinates, and the theta is the opening of the angle here. So this is the basic idea. Again, I show you here how to cut that element from the moving fluid like this. So we cut at this area and we make it 3D. And then this is another diagram to show you the direction of axis in polar coordinate. The z here is the height or the depth of the rotational motion here. So we have the radial here, we call it r direction. So r here is for the radial direction here, and then we assume that this molecule is moving like this. So we could say that at this point we could calculate the tangent velocity here, and this motion is at theta direction. So we have a three direction here: the radial direction, the radial axis, the theta axis, and the z axis. Okay, we need to derive continuity equation based on this diagram, and this is the axis diagram for this particle. The idea is still the same with the derivation of continuity equation for Cartesian coordinate, The net flux of mass entering the element equal to the rate of change of the mass of the element. So we could write mass flow rate at inlet minus mass flow rate at outlet equal to changes of mass in terms of time, dm dt. And mass flow rate is written as m dot, and the equation to calculate the mass flow rate is rho, A, and V. Rho is the density of fluid, A is the cross-sectional, and V is the velocity of fluid. First, to simplify our calculation, we will calculate the mass flow rate at inlet and outlet for one single axis. For example, for here, we are calculating the mass flow rate for the direction of R. So here, this is the direction of R at this direction. So the mass flow rate at inlet is here, and the mass flow rate at outlet is from this surface to the outside direction here. For mass flow rate at inlet here, we could calculate by using the equation of rho, A, and V. So rho is the rho of fluid, and A here is the cross-sectional area. So from this surface, we could calculate the cross-sectional area here is R d theta, mean the length of this one times dz, mean the height of this surface. You could see here is R d theta dz, means this is the area of this one. R d theta is length of this one, and dz is the height of the surface. So R d theta dz is the area of the inlet, and times VR. VR is the velocity at inlet in R direction. Then we minus with mass flow rate at outlet. So this is the surface of outlet. So we could calculate the cross-section area here by using this equation. R plus dr, because the distance here is R plus dr, times d theta, because R plus dr is the length of the radius. We times d theta to get the distance here, and then we time with dz, the thickness of this element, to get the cross-sectional area at the outlet. So this R plus dr, d theta dz, is showing the cross-sectional area at the outlet. And for the velocity and density at the outlet here, as we mentioned or as we described in Cartesian coordinate previously, we don't know which parameter will be changed, whether density or velocity. Because of we have possibility to have changes in density and velocity, so we use the idea of partial derivation. So we write rho VR plus del over dr, rho VR dr. So this is the mass flow rate, the total mass flow rate at R direction. So we solve this equation. At the same time, we could neglect the small value. For example, if we get dr times dr, so we could assume it is equal to 0 because it is too small, and then we could have this term, and then we could simplify this term into negative del over del r rho VR r dr d theta dz for the total mass flow rate at z direction. Please try to do this at home. Next, we are calculating the mass flow rate at z direction. So this is the z direction, means this is the inlet flow, and the outlet will come from this surface to the out direction like this. So the inlet here is rho Vz r d theta dr. So rho is the density, Vz is the velocity, and r d theta dr is the cross-sectional area. Let's see. So r d theta is the distance of this one, and dr is the distance of this length. So means r d theta dr is the area of this one. So because this element is very small, it is okay for us to calculate the area here by using the equation of square. So we just multiply the length here with the length of this one to get the total area for this element. And then for the mass flow rate outlet here, again r d theta dr is remain the cross-sectional area at outlet. Because there are no changes, so we use the same term for the inlet and the outlet here, r d theta dr. And then we could write rho Vz plus del Z rho Vz dz, because the changes at the outlet here might be come from density or velocity, or might be both parameter density and velocity will change. So we solve this equation, we get minus del over del z rho Vz r d theta dr dz. Next, we calculating the mass flow rate in the direction of theta, the angle here. So means that you could imagine that we have the inlet from here to here, and the outlet is from this surface go forward like this. So the mass flow rate and inlet here is calculating by using the same equation, rho AV. So means that the rho here is the density, the velocity is v theta, and dz dr is the cross-sectional area. So we have the dr here, and we have the dz here. So this is the cross-sectional area at inlet, and we also have dr dz for the cross-sectional area at outlet. So it is okay for you to write dz dr or dr dz. And then the mass flow rate that comes out here, the changes can be written as rho v theta plus del over del theta rho v theta d theta. And then we could simplify this term into negative del over del theta rho v theta d theta dr and dz. Next, we are calculating the mass for the particle here. Mass can be calculated by using rho times volume, and rho here and the volume is r d theta, mean the distance of here, times dr, mean the distance of here, and times dz here. It is okay to simplify the calculation of volume for this particle by using the idea to calculate the volume of a cube. So please remember this simplification. So we have dm over dt. So we substitute the value of m that we get here. We could have del over del t, rho r d theta dr and dz. And now we take this equation, mass flow rate at inlet minus mass flow rate at outlet equal del t m element. We substitute all the value here with the value that we get in previous calculation. So this is the total mass flow rate for r direction. So this is mass flow rate for the z direction, and this is the mass flow rate at theta direction, and this is the value of mass for that element. We substitute, and then we divide this term with d theta dr dz. We could get this equation. And then for the right hand side equation, del t rho r here, we could expand the equation, become rho del r over del t plus r del rho over del t. So here the value of del r over del t is equal to 0. It is because The meaning of del r over del t is the changes of radius regarding to the time. So according to this diagram, and for sure the radius value here is not increased according to time, so we could say that the rdt is now equal to 0 because there are no changes of r regarding to the times. Now we could have our continuity equation like this. So, and then we could simplify this term by dividing all terms here with r, and we get this term. And this is the basic continuity equation for polar coordinates. That I hope you could remember this equation, and the best you could derive your own continuity equation by imagining this cube and this axis. So the compressible equation for continuity in cylindrical polar coordinates is del rho over del t plus 1 over r del r rho vrr plus del over del z rho vz plus 1 over r del over del theta rho v theta. If we are only focusing on two-dimensional, an incompressible fluid means there is no changes in density and the velocity of z direction is equal to 0, the continuity equation can be written like this. There are no changes of density, so we could assume that del rho over del t here is equal to 0. Then we could neglect the value of Vz because there are no velocity of z here, so we reduce the term of Vz, and then if we expand the value here, so we could find it is equal to 1 over r del Vr dr plus 1 over r del r del r over dr, and then we could simplify it into Vr over r only. So we have a del Vr over dr plus 1 over r del V theta over d theta. Okay, so this is the final equation for continuity equation for 2D and incompressible fluid. In some textbook, they will use the terms of or the symbol of U prime and V prime to represent the value of Vr and V theta. However, in our syllabus, we will use Vr and V theta for our calculation. Please use Vr and V theta in your calculation.